All right, hello and welcome to the short intro video on section 5.3. This section of the book covers two extremely important theorems. There is a third theorem that is covered in the book in this chapter, but it's not going to play a particularly big role for us because we're not going to ask you to estimate the remaining terms based on the remainder theorem. So, without further ado, let's get into it. The first theorem that this section covers is the so-called divergence test. This is, I think, easily one of the most important theorems relating to the convergence or divergence of an infinite series. It will almost never apply, but when it does apply, you're done. So what this says, the theorem says, so theorem, remember being sort of a phrase for a big math result. If the infinite series of an converges, then we must have that the ANs themselves as a sequence. That's a little bit weird because we don't often talk about the terms of the series as a sequence, but if we do, the limit must tend to zero. The proof of this theorem is actually quite easy, but it's a really nice little opportunity to review some, or very quickly, what it means for an infinite series to converge. So remember to say that the summation from n equals 1 to infinity of an equals some limit L, means that the sequence, I'm going to write this in a different color because it's that important, that the sequence of partial sums, which we typically denote SK, converges to L. This is how we defined what it means for an infinite series to converge. It means that the sequence of partial sums of that series converges to L. And so in particular, and this is a useful little feature that I don't know if the book calls attention to, the nth term of the series is nothing other than the nth partial sum minus the n minus first partial sum. I just want to point out, it's a really useful little observation. It's completely definitional. But if you think about it, what is Sn? It's the sum of all of the terms up to n. And what's Sn minus 1? It's the sum of the first n minus 1 terms. So what's the difference between those? The sum of the first n terms minus the sum of the first n minus 1 terms. The difference is just that last nth term. And that's what this is saying. So in particular, from this, we can see that the limit as n goes to infinity, and this is exactly the proof that's in your book. It's exactly the proof that's in every calc textbook, because I don't know why you'd ever have to work harder than this. But I'm not doing anything particularly deep here. I'm just regurgitating the book's proof. But again, highlighting the features of this proof that I really like, is by definition then the limit as n goes to infinity of Sn minus Sn minus 1, but by a beautiful property of limits, as long as we know the limits exist, which in this case we do, the limit of the difference is the difference of the limits. But both of those sequences, they're the same sequence. You've just shifted one back. So this is just L minus L, and hence you get 0. And that completes the proof. That's a little math symbol for completing a proof. So I want to say real quick, this theorem is fantastic because when it works, you're done immediately. Let's do a very simple example to highlight how this can tell us something. So a question might look something like, does summation from n minus 1 or n equals 1 to infinity of, I don't know, say 2n over 3n minus 1. So I guess I need to, yeah, we're good. Converge. Does this converge? And you're going to get a lot of questions later on later assessments that look exactly like this. Well, in this case, here is my an, and we can immediately see that the limit as n goes to infinity of an is equal to 2/3, which is not 0. So we can immediately conclude, no, the series diverges. Now I want to point out the most important part of this theorem is what it doesn't say. So it is extraordinarily useful if you get a situation like this, where the terms don't tend to, the summands themselves, considered as a sequence, don't converge to 0, you're done. That's simple. But what this doesn't say, and what you have to be so careful about messing up, it does not say that if the terms go to 0, then the series converges. Crucially, it is not called the convergence test. It's called the divergence test because it can only tell us when something diverges. So a good example to keep in mind, the harmonic series, 1 over n, this series diverges despite, that's the key word here, despite that the limit as n goes to infinity of 1 over n does equal 0. So you cannot flip this around. But what it says is that if the terms don't go to 0, then the series cannot converge. I guess technically that's slightly an equivalent but slightly different way than I originally stated. So let me say that one more time. So the way we wrote this and the way it's stated in your book initially is that if the series converges, then the limit has to be 0. The logically equivalent statement to that, something called the contrapositive, is that if the terms do not go to 0, then the series has to diverge.